Hello, everyone. Um, so today we are going to begin module 2. This is session 4 in the course on exploratory data analysis. The first session as part of module 2. In this session, we are going to take our discussions forward on by talking about the choice of statistical tests and some assumptions underlying those tests. So we begin with some preliminary concepts on hypothesis testing. This is only pertaining to exploratory data analysis. We'll not go in detail. We'll talk just about some steps that are involved and how what step of hypothesis testing is crucial for exploratory data analysis. We'll talk about what exactly a statistical test is. Uh, we'll talk about how the research question governs the choice of statistical tests. We'll talk about certain underlying assumptions for various statistical tests and a quick overview of parametric versus non-parametric tests. So we have talked about the research process before, and we looked at that basically the process of research starts with the identification of your outcome or the dependent variable, and the choice of the independent variable in terms of how change in the independent variable will lead to, in terms of maybe associated with or cause a change in your outcome or dependent variable. We had briefly touched upon what were different processes for formulating research questions, the various frameworks, and then we convert uh, these research questions into testable hypothesis. Testable in terms of the data that we collect. The only way that we have to test them is by observing the data related to a research question and then testing our research questions which are formulated in terms of hypothesis. This Once we collect data, this is followed by an exploration of the dependent variable type and distribution. We looked at it in our very first session where we talked about, the levels of measurements and the distributions of dependent variables, whether they are skewed, they are not skewed. And the different shapes that were possible. We talked about in session 2 and 3 about the choice of metrics to summarize in terms of the mean, standard deviation, the median, and the interquartile range, and how the distribution and level of measurement affects the choice of these metrics. This is then followed by, once you've made these choices in terms of the level of measurement, exploring distributions, and summarizing these with various metrics. When you look at the associated hypothesis with the research question, the next thing you think about is what is the most appropriate statistical test? That is, what can I do with my data in order to ascertain whether my hypothesis is true or not, or do I have enough evidence to accept accept or reject the hypothesis that I have started out with. So you choose the statistical test, and every statistical test has some or the other underlying assumption. Um, a statistical tests or statistical models are always an approximation of reality. They use real world data to create approximate models. So they are always based on certain underlying assumptions. We cannot model the entire of reality. If we were able to, it would we would perhaps not the need for statistics. So it's always Statistical models are approximations of reality. They are always based on certain assumptions, because a lot in real world phenomena may not be known. So we make assumptions about the unknown. Then we conduct the test if the assumptions are reasonably met, else we choose alternatives. So you may start off by saying that I have two groups and I'm going to compare them using, let's say, a t-test. Then you go about verifying your assumptions of the t-test and you realize, okay, maybe that my data does not follow the assumptions that are required for the t-test. So what are the alternatives that are available to me, given that I can apply my data to answer the same research question? So that's the entire, and once you get the output of the test, you interpret it, and then you reach the conclusion regarding, do you have enough evidence to accept or reject. Then, so what exactly is a hypothesis test? So a hypothesis test is a claim made about the unknown population parameters and has to be tested based on a single sample drawn from population under consideration. So this is a very broad overarching definition. So what do we mean by unknown population parameters? So generally, our research question will be formulated in a way where we can, as we saw in the previous slide, we have to convert it into something testable. And you can test only something that can be calculated from the data. So for example, you have a very generic research question which says that you are interested in knowing if obesity as an outcome is related to your nutritional intake. So now obesity as an outcome probably is measured in terms of fat mass or BMI, and uh, the data that you collect will be in the form of either raw weight, height values, and calculated raw BMI. And so with that, the unknown parameter that you are basically looking at may either be the raw average, the average BMI in your target population, or if you define your outcome as categories of BMI, then it would be a categorical variable as a measure of obesity. So the unknown population parameter, you make a claim about it that let's say your sample comes from a population with a BMI of 21. So the unknown parameter is the mean BMI, and you have to take one single sample. Obviously, you can't draw many samples practically. Theoretically, you can, but practically, you have a single sample on which you have to base your on which your evidence will be based. So hypothesis testing is generally about this unknown parameter. This parameter can be an average. This unknown parameter can be a proportion. It can be a correlation coefficient. So, or the rate of change. It can be the rate of change. So the hypothesis is about, generally about one of these things. Or it can be a percentage, like. So, how these are just some examples of how different kinds of research questions can be converted to testable hypotheses. So, so let's say if your overarching research question is drug A as effective and safe in reducing blood pressure as compared to drug B? So one of the ways you could test for the effectiveness would be the mean reduction in BP from baseline between drug and drug B. It is greater than 0. And in terms of safety, you say that the incidence of headache among patients getting drug A is lower than those getting B. So you can see the two different metrics to define these outcomes. The research question was a generic statement, but when you converted it into a testable hypothesis, you were talking about concrete measures that you can calculate from the data that you can collect. So second question, is the prevalence of thalassemia in India at same levels as the Middle East? This is generally a generic question when you're talking about research questions that are looking at, new diseases or um, uh, populations with, specific vulnerable populations in which you are trying to understand the presence of a disease. So this research question overarchingly could be in the form of a prevalence or in the form of an incidence. Has the incidence of thalassemia changed over time over the past 15 years. So this is a second type of research question where you would want to convert it into a testable hypothesis in the form of the percentage of thalassemia patients in a sample from India is 1%. 1%, why? Because it could be this target number that you have, whatever 1x%, let's say, would be the value that you get from your reference population that you're comparing it to. So again, you have a very testable metric that you can calculate from your data. And then, does spending time outdoors influence how satisfied people feel with their lives? Very generic, overarching questions, but you get the way you would convert. Possible conversion would be, how do you measure satisfaction? You would have some metric for measuring satisfaction. So the outcome is satisfaction. Your independent variable is the time spent outdoors. So uh, the way you could convert it into a testable hypothesis is there is a significant positive relationship between the weekly amount of time. So here you are quantifying the independent variable in terms of weekly amount of time. So it would be in hours, so minutes or whatever, or number of days in the week. And self-reported levels of satisfaction with life, where you would be using some known scale, which will give you some kind of a score. So that's how these are some ways you can make your research question and convert it into a testable hypothesis. And it becomes testable when you formulate it or convert it in a way where you are getting a metric that you can get from the data. Obviously, the choice of the metric will be based, number one, on existing literature, so that you can make your results comparable with what has been done before. So that's one governing choice. And the second could be in terms of what is your context, in your context, whatever is the measurement that is generally chosen. So broadly, there are the following hypothesis type. So the first, the simplest one is, does my sample come from population having a specific value? So for example, in the thalassemia example, we had whether the thalassemia levels in India compare to a specific target, a specific reference population. So you might be interested in knowing something like that. So another example would be, does your sample come from a population of hypertensives, that is having a mean blood pressure of, let's say, 150 by 100. So 140 by 90, or so. That's first example. Then in the second example, you take it a notch further. Are two groups in my population same based on the characteristic of interest? So you might be looking at gender differences, and your testable metric could be in terms of, let's say, the average BMI levels, average blood pressure levels between the two, or the proportion of males with blood pressure control versus the proportion of females with blood pressure controls. Or if it's a generational comparison, age group less than 25 and age group greater than 25, or disparate age groups in terms of young adults less than equal to 22, 25-year age groups versus greater than 45-year age groups, and how their quality of life scores or satisfaction scores or job satisfaction levels, or some kind of life quality indicators, they are different between two groups. And then a more extending this case too is, instead of having two groups, you have multiple groups, more than two groups. Again, you might be interested in comparing averages or proportions between these multiple groups. And then the last, which is the very overarching case, and case 1, 2, and 3 are actually special cases of the fourth kind of hypothesis. So it says that are exposure variables associated with outcome of interest. So here we are looking at questions like, does a certain intervention versus control impact, let's say, mortality? Um, uh, and this could be more causative, or it could simply be association, like, does change in temperature influence bone health? Um, so these kinds of hypotheses, in which you use techniques like modeling, where you have not only one variable, but you are looking at, let's say, multiple variables that may associated with your outcome of interest, and you are trying to test the hypothesis with statements like, what are the risk factors, or in terms of, so what are the socio-demographic characteristics that influence a certain health outcome. So you make it testable by looking at the rates of change, which are nothing but the slopes of regression equation. So then, what is a statistical test? Once you've know your hypothesis, you've converted it into a testable statement, you know what are the metrics that you will be calculating, then you have to look at a statistical test. A statistical test provides a mechanism for making quantitative decisions about a process or processes. And the intent is to determine whether there is enough evidence to reject a conjecture or hypothesis about the process. So ideally, it's a set of procedures. That entire set of procedures, we are going to look at this set of procedures in a while. So this entire set of procedures, where you take the data that you have observed, you convert it in some kind of metrics, and then you compare it to some known standard value, and then based on that known standard value, you take a decision regarding, do I have enough evidence in my data to um, reject the hypothesis, or um, uh, the status quo, which we call the null hypothesis, which is, in the context of these four research questions, it would simply be, in the context of the first research question, a null would simply be that your population prevalence or proportion is equal to a specified value, versus that it is not equal to, either greater than or less than. In the second, it would be that, another two, the null would be that both groups are equal in terms of the characteristics that you are comparing them with. And third, all three are equal, versus at least one of them is different. And in the fourth, it would be, the test would basically try to ascertain whether the rate of change is zero, or it is positive or negative, and whether it is significant or not. So you see how much evidence you have um, uh, uh, supporting your null, and whether you have enough evidence to reject it. So what is the information you need? So statistical inference is the act of generalizing from a sample to a population with a calculated degree of certainty. Now, once you do a statistical test, the whole idea is that you are trying to ascertain something unknown about your target population. And what is that unknown? That unknown is called the parameter. And from your sample, you try to calculate that equivalent of that parameter. So if you're trying to estimate an unknown population mean, you calculate the corresponding mean from the sample. If it is a proportion that you're trying to estimate, then proportion is what you calculate from your sample. And then you convert it into a metric, which we call that statistic. And that is the statistic that we use for testing our hypothesis. So this is the entire testing process for any kind of test. These are the steps that we generally adopt. So you formulate the null or status quo, that is the null hypothesis. That is, in the absence of evidence, what is the current situation that you would go for? And then your claim, which is the alternate hypothesis. So then you identify the test statistic that is and its appropriate distribution. Why do you need its appropriate distribution? Because, as I said, the test statistic, once we say statistic, Statistic is a quantity that you calculate from the sample that you have collected. So there is a clear demarcation. What you don't know about the population is called the parameter. What you can calculate from the data is called the statistic. So that is why we say test statistic, because every value in this is calculated from the data that you have and the value that you have assumed about the reference population or the null value. So, and then we look at its approximate distribution, which is generally a theoretical distribution. The reason why we have to have knowledge about its appropriate distribution is also that once we have calculated the value of the test statistic, we need to compare it to some known standard values. And when we compare it to those known standard values, is the point where we can decide whether we have enough evidence or not to reject. So the next step is to fix the type 1 and type 2 error. This is beyond the scope of this exploratory data analysis and will not veer into this discussion, but these are essentially related to metrics of uncertainty. So when you're taking a decision based on a sample, there is always a chance. It is not based on all the target population values that are of interest to you. They are always based on a sample. And somebody else doing the same study may arrive at a different kind of a sample and get a different result. So there is always a chance of making an error that you are either incorrectly rejecting the null hypothesis or, so these are the errors of related to the uncertainty that comes with choosing a sample. So, but you fix one of these in advance, and then you collect data and calculate the test statistic value. You compare the calculated value to the critical value. This critical value is what you get from this appropriate distribution, the distribution of the test statistic, which is like the standard which you compare your sample value with. And then this also helps you ascertain the p-value or the calculated probability, and you benchmark this p-value against the known critical value. So this is the entire process. In this entire process, the part that we are interested in with respect to exploratory data analysis is to identify the test statistic and its appropriate distribution. And this appropriate distribution will always be based on certain assumptions. So how do we choose an appropriate test? There are four pillars to choosing an appropriate test, and the first is, the number of variables, because the number of variables will determine whether you are doing a univariate analysis or you're doing a bivariate. Bivariate means looking at an association between two variables, or a multivariate, which is more generic. That means you have multiple independent variables or exposure variables, and you're trying to look at the association with the outcome of interest. And a univariate would simply be, let's say you are just looking at the distribution of BMI values and you want to compare them with some known value. So number of variables is important. Then the study design is extremely important because whether you are using an unpaired or a paired sample, if the individuals that you are studying differs over time, or different kind of groups, so let's say gender differences, unpaired sample, because you're looking at a set of males and a set of females, unless and until these individuals have everything else in common apart from their gender, so they are generally considered as unpaired samples. So test for unpaired versus paired samples are different. So paired samples would be things like two different sets of people, but they are rating the same thing, exactly the same thing. And we are looking at, let's say, the discordance and concordance between their ratings. Or a paired sample could be like a pre and post kind of a study design, where or a crossover kind of a study design, where one intervention is given to people. They are observed for a certain duration, the outcome is observed, then there is a washout period, and then the same set of individuals is exposed to another intervention. Or you could just have a pre and post surgery kind of a situation. So in these cases also, the tend to be different. Then other kind of designs are where they are looking at repeated measures, of which paired or a pre-post design is an example, or multiple follow-up period uh, will also determine the choice of a different kind of test. Then the two main important things that we have been continuously discussing, which is the level of measurement, whether you are looking at categorical binary variables as outcomes, or continuous variables, will determine the choice of test. How is your outcome variable distributed? Is it symmetric? Is it asymmetric? In which direction does the asymmetry go? Do we know about the shape of the distribution, or we don't know about the shape of the distribution? So these are the four key things that can help you, that once you've converted your research question into a testable hypothesis, these can be your guiding, guidelines as to um, how do you start thinking about what test I can choose. And you might have multiple alternatives, and then you make a choice again based on certain uh, considerations, which may be based on very practical considerations that you are seeing in your field or with respect to your data. So this is just kind of a guiding flow chart, which helps you understand, or kind of a process flow, which can help you choose a test. So if you have a continuous endpoint, continuous outcome, and you have two choices, and these two choices again are governed by what do you know about the distribution of that outcome, or even if you know about the distribution of the outcome, is that distribution violating some kind of a assumption that you of the test that you have originally thought of? So in with respect to this, we come across parametric versus non-parametric as terminology. Now simply speaking, the parametric distributions are used when you know the shape of the distribution of your outcome variable. There is some known shape like a normal distribution, a T and Fn distributions. The reason they are called parametric is because we know how their shape and central parameter looks like, and that helps us to use them as benchmarking distributions. So we know what the 95% interval of these kind of distributions will look like. So we can compare the results that we get from our data to these standard benchmarks. So that is why they are called parametric. The non-parametric are there. We might be looking at a quantity or an outcome that we don't know the distribution about. Sorry, in the context that we are studying. So, for example, let's say quality of life. In our context, let's say we don't know how the distribution is. We don't know if it is symmetric or not symmetric, what kind of a shape it has. So, a wise choice would be to look at a non-parametric tests. Or sometimes when you are looking at categorical and ordinal and nominal outcomes, a wise choice would be to go for non-parametric tests. In parametric also, again, the design of the study, if it's a paired or an unpaired design, if it's a paired, um, you can use something called a two-group paired t-test, or you can use an analysis of variance. We are not going to go into the technique of these. We have shared reading material with respect to the technique, but the important thing is the guiding principles that can help you decide um, what to choose. So similarly for unpaired, you can have the unpaired t-test and the analysis of variance again. In the paired case for the analysis of variance, you can, because for greater than two groups, it would be a repeated measures analysis of variance, where you have assumptions about the structure and the correlations between the pairs of observations. For non-parametric also, the design whether it is a paired or unpaired sample will determine what are the kind of tests we can use. And for example, for the unpaired case, you have Mann-Whitney U test, you have uh, 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 for greater than two groups, you have the Kruskal-Wilkes test, and you have the corresponding post hoc tests also. So, for example, we know that when you do an analysis of variance, the hypothesis you are testing is whether all the groups are same in terms of their means, or at least one of those groups is different. And the primary hypothesis, if it is, let's say, the null hypothesis is rejected, you don't have enough evidence to accept it. And so what you do is, the next step that you do is like a post hoc test, and you then determine which of the groups is significantly different. So similarly, you have the non-parametric equivalents also. So for all the parametric equivalents, you do have the non-parametric equivalents. However, uh, generally, you'll see in literature that parametric tests are preferred. One is in terms of the interpretability, the metrics and the estimates that you get are very easily interpretable. Also, parametric tests are more powerful as compared to non-parametric tests, in the sense that their ability to detect the effect that you are trying to detect is much better as compared to non-parametric tests, because you know the distribution that you are comparing your data to. It is a known shape and all. So for categorical data, these are some of the options that you have. As a process flow, which you can use, step-by-step process flow, to as a guiding flow chart to make a decision regarding what is the test you can use in order to answer your question when you have categorical data as your outcome variable. Now, what are some of the common assumptions? As I said, assumptions are very important and they should be reasonably met. Some amount of violation may be okay, but in general, some of these tests have quite stringent assumption, and it is good to verify if those assumptions are met, because otherwise the effect estimates that you might be getting as a result of these tests, and also the significance and non-significance p-values that you might be getting, might be biased and incorrect. So some of the common assumptions are that the dependent or the outcome variable of interest has a symmetric or normal distribution at the population level. What this means is that, for example, if you are taking your hypothesis is related to weight gain or weight in a certain age group, you might know that weight gain in the population for that age group has a normal or a symmetric distribution, where most of the individual average weight gain hovers around a certain value, let's say 10 kilograms, and then all the other individuals are equally distributed on both sides of this average gain value of 10 kgs. So because you know that at the population level, the characteristic that you are studying is normally distributed, you have a lot of parametric tests available to you. So if you are doing, let's say, that the weight, your hypothesis is that the weight gain is equal to a specific value, you can use the Z test. If you are doing a comparison between males and females, male young adults versus female young adults having a weight gain, comparing their weight gains, then you can use the t-test, which has assumptions that the characteristic that you are studying comes from a normal population in the two groups. Then the second assumption is the spread or variability of the outcomes across various categories or values of the independent variables is similar. And the name given to this phenomena is called homoscedasticity when you are talking about equal variance, or you call it heteroscedasticity. Now, without going much into the nomenclature, it simply means that, let's say, Again, we're taking the weight gain example. If you're looking at weight gain across age groups, what it means is that if, let's say, your age group is 18 to 25, and then 25 to 45, and then greater than 45, that is your exposure variable age group as these three categories. What the heteroscedasticity assumption means is that the outcome, which is the weight gain, in order to find the true effect of the difference between the average weight gain between these three groups, the spread of this outcome should be the same across these groups. Because if there is a lot of variability between the outcomes across these three groups, the true effect, which is the mean, you will not be able to detect it, because there will be a lot of noise in that will be associated with the true effect. And then the third assumption is that the relationship between the dependent and independent variable is linear. This is especially true when you are looking at, you have a continuous outcome, and the first idea that would come to your mind is, okay, because my outcome is continuous, irrespective of what my independent variables are, whether they are categorical or continuous, I'm going to look at a linear regression in order to answer the research question: what is the most important risk factor associated with my outcome? So, common tests that you will see in literature, in almost every paper, you will come across terms like the t-test and the chi-square test. The chi-square test, for example, when you're looking at baseline characteristic tables in any research paper, it will be accompanied by a chi-square test, especially if you're looking at, let's say, baseline characteristics between intervention groups, and your characteristics of interest are also categorical. And obviously, the intervention groups have categories like placebo or drug, or intervention A versus intervention B. So you have these tests, and uh, you also have linear regression analysis as a very common output, where you will have tables that have the beta estimates and the standard errors. Now, these have underlying assumptions. For example, when you do a t-test, uh, uh, you do have t-test versions where you have t-tests with equal variances in both groups versus unequal variances, and you can adjust in the unequal variances version, will adjust for a factor to adjust for the noise that comes because of the unequal spread of the distribution of the outcome in the two groups. But the stringent assumption is that whatever characteristic you want to compare between the two groups, ideally it should come from a population where that same characteristic is known to be normally distributed. So that is an assumption that we should verify. And we have one of the very good ways, which we have discussed in previous session, to see if the two groups are normally distributed. One is, we could look at a QQ plot, and the other is, we could look at box plots or between the two groups. So if you are looking at, let's say, gender differences in weight gain, all we need to do is make a box plot of weight gain by group, by male and female, and see if there is a fair degree of asymmetry. And the next thing we do is, we see whether the asymmetry is due to outliers. Are these outliers errors or not? If there are errors, we remove, and then we apply the t-test if your data becomes normal for both groups. But if it's not, again, then there might be some very valid reason for the distribution of weight gain to be skewed in both the groups. And then, rather than use the t-test, I mean, the very first option, which we will discuss in a couple of minutes, is to transform and make it normal, or we can apply some non-parametric, equivalent non-parametric test for comparing gender differences in weight gain. For chi-square test, we'll look at the assumptions in a short while as an example. For linear regression analysis, again, in the previous session itself, we have looked at metrics that we can use to verify these assumptions. So linear regression, the error terms, which is the difference between the observed and the expected value, those error terms should be normally distributed, is one important assumption. The second is, obviously, there should be a linear relationship, and the best way to look at it is, through matrix plots or graphs. Um, so coming to the chi-square test example. So one of the very common, as I said, it's such a commonly used test, but little known that there are assumptions underlying these tests also. So one of the assumption is that that data in the cells should be frequencies or counts. So never apply chi-square test when you have your data as the form of percentages. Um, then the second assumption is the level or categories of the variables should be mutually exclusive. So if you have, let's say, age groups as a categorical variable for one of your exposures in the chi-square test, then they should be mutually exclusive. Obviously, person belongs to one age group should not be there in another age group. Or when you're looking at intervention groups, a person who is getting intervention A should not be getting intervention B also at the same time if you are looking at the relationship. So they should be mutually exclusive categories. Um, and then each subject may contribute data to one and only one cell in the chi-square. Then the fourth assumption is the study groups must be independent. So obviously, the response of participants who are getting an intervention A or who have ex, exposure category belong to the first exposure category, their response should be totally independent of the response that is given by individuals belonging to exposure category 2 or getting another intervention. So this is called the independence, independently distributed. And we know that in the chi-square test, we have a table which, the contingency table that we prepare gives us the observed cell frequencies, and the test statistic is calculated based on the difference between the observed and the expected. So the value of the first step that we do in a chi-square is to calculate the expected cell frequencies, and the assumption is that the expected cell frequencies should be 5 or more in at least 80% of the cells. So if it is not, the thing is that this chi-square, which is a continuous distribution, its continuity is destroyed. And so the criterion that at least 80% of the cells, so if you are looking at, let's say, a 2x2 table, you would want at least, all four of them to have cell frequencies of 5 or more. Um, and no cell should have an expected of less than 1. Obviously, zero cell frequencies will not give you the correct p-value for the independence for which the chi-square test is used. And then you have an alternative, which is to use the Fisher's exact test, or even when the cell frequency is less than 1, you cannot apply any other kind of a correction factor. Um, so these are some of the assumptions of the very well known and commonly used chi-square test. And you will see, a lot of literature. In fact, there are references that have done reviews on chi-square test reporting, and you will see that there will be several publications that report chi-square tests even when the cell frequencies are less than 1 or less than 5. That is incorrect. You can consider using the Fisher's exact test, and this has implications specifically, especially when you're doing modeling processes like the logistic regression later, because if you've gone ahead and not verified this assumption, these can lead to highly biased and incorrect odds ratios when you're doing modeling. Now, coming to an example here, just the application of the chi-square test is this is a 3x2 contingency table where we are looking at vaccination as an exposure, and the status of sickness with respect to pneumonia. Around 92 patients total were vaccinated and unvaccinated, and the outcomes were compared for these outcomes in terms of whether they were sick with pneumonia, or they were sick with non-pneumococcal pneumonia, or they just did not have pneumonia at all. So when we perform, we know that here one of the cells has a cell frequency of 5. So this is 1 out of 6 cells. So obviously it's much less than 80%. We can go ahead with doing the chi-square test. And so we count the expected cell frequencies. You can the calculation process is there in the notes section that will be shared, but you get the expected cell frequencies. So the numbers outside the brackets are the expected cell frequencies, and the numbers inside the brackets are the corresponding chi-square values. So cell frequency is nothing. So 13.92 is obtained by multiplying 23 with the marginal total. The marginal total is 28, and row total, and the marginal column total for unvaccinated is 92. So you multiply 92 and 28 and divide it with the total number of samples, which is 184. That's how you get the cell frequency, expected cell frequency corresponding to 23. And for 5, for example, it will be 92 multiplied by 28 divided by total number. So that's how you get the corresponding cell frequencies. And once you do that, the expected chi-square value that you get is the observed minus the expected value. Ideally, the contingency tables for each in a contingency table corresponding to each cell, you should have the corresponding chi-square value, because it's a very good indicator of the inequality of proportions across groups. And this is the point where you can ascertain which of these specific categories is significantly different also. So we see here, let's say the chi-square value of 5.92 already tells us that there is a huge discrepancy between the observed and what you expect in this particular uh, in this particular cell. So patients who are sick with pneumococcal pneumonia and who are not vaccinated, there's a huge difference between what you actually observe and what you would have expected. And this here itself tells you the significant association between vaccination status and sickness with pneumococcal pneumonia. The other assumptions that we have are normality and linearity. Um, Normality and linearity are stringent assumptions when you are looking at tests like analysis of variance and regression. We have already looked at techniques for these, some of the techniques that we can use to identify departure from normality and linearity. So we'll talk about what to do when there is a departure from normality. We have certain alternatives that we can use, and let's consider what we can use and when. So as I said, we've looked at this graphic before. So a very good way to identify linearity is looking at the potential independent variables and the outcome variables and plotting if they are continuous. Good idea is to do a matrix graph like this, the one on the left hand side, or doing the one on the right, which also gives you across the diagonal, you have the univariate distribution of each of the variables. And you can look at the main outcome variable and identify whether there is a departure from a symmetry over there. You can give skewness and kurtosis statistics and identify the degree of skewness, departure from symmetry. And this also tells you whether you have a linear relationship, and so you can put you can apply the straight line linear regression equation, or you need to consider number one, either the independent variable should be included as a polynomial term or some transformed term like a square term or a cube term, or you need to look at a totally different kind of a relationship, not a linear one, but like a curvilinear relationship. So these scatter plots are very, very informative to identify departure from linearity and the potential patterns, alternative patterns that you can model the relationship on. So the other option when you have non-normality is to transform. So transformations can be used for different purposes. Uh, so the very first transform, and we have looked at this in a previous session, is a z-score, which is nothing but you subtract the mean from the raw value and divide by the standard deviation. This is a transformation that is used primarily for convenience and comparability, which means that in your regression equation, let's say you have CD4 counts as one of your exposure variables, which we know can have, very small values starting from, let's say, 100 and 150, and then going on to 10 to the power 7 digits. So, and then you have another variable, let's say, population density or something like that in the same, and that has more narrower set of units. So or let's say blood pressure, which may have a narrower set of units. Now you are comparing, you are using as independent variables different variables that are measured on hugely varying scales. So one option is to transform the data using z scores, all the independent variables converted into z scores, and then um, uh, you apply your model. Or you can also convert your outcome variable, which is measured in a very wide range scale, and convert it into scale it down to z scores. This is very, very commonly used when you are looking at anthropometry, especially when you are doing reference ranges of, let's say, um, weight gain in neonates, or you're looking at, let's say, head circumference, arm circumference in neonates. So these scores are good transformation techniques to scale down. Then the other set of transformations that we can use to convert non-normal data into fairly normal distributions is the log transform. Um, the idea is, if your data is right skewed to reduce skewness, it can also used for linearizing the data and to make it additive so that we can apply the linear regression model. So examples in literature, you will find a lot serum albumin, rather than use the raw values of serum albumin, they are often log transformed. By log transforming, they become fairly normal, and then you can apply linear regression, you can apply t-tests to serum albumin levels. Similarly, fasting blood sugar levels also known to be fairly non-normal, and by log transformations, they become normal. So here is an example where you can see that the graphic on the right, the original raw distribution of the data, it has a lot of, it's heavily right skewed, and you have a lot of individuals having values just a little greater than 0. And scale is very wide, but the moment you log transform and you see the distributions, it becomes fairly normal, and then you can apply your parametric tests to this. However, the disadvantage of the log transformation is that, if your data, your raw values have 0 as an outcome, a lot of people have responded as 0, and 0 probably means something, then and then you would not use a log transform. It would practically be meaningless, and you would not be able to transform. In that case, the option is either you use a technique that is more pertinent to the skewed data itself, because your natural, let's say, the natural distribution of the data itself is that, um, and you might consider using a non-parametric method. Then here you see by linearizing. So you're looking at the relationship between, let's say, GDP per capita on the x-axis, and the percentage population, or both in the raw scale. And we see that the distribution is not linear. So is there a way to linearize the relationship? Because by linearizing the relationship, it becomes easier to interpret. We know that linear regression coefficients, the slope and the intercept, they actually have a proper interpretation. So the slope B essentially is the rate of change in the outcome for 1 unit change in X. And the intercept A is the expected value of the outcome in the absence of any independent variable. So overall expected value of the outcome. So they are very easy to interpret. So most researchers to get a parsimonious model, if it is linearizable, we can use transformations to linearize it and then use the interpretation of the linear regression model, the slope and the intercept coefficient. So, for example, here the GDP has been converted to the log scale, and then when you replot the scatter plot with the log GDP and the percentage population, urban population, so you get a linear kind of relationship. So when you do the regression now, your outcome variable is percentage urban population, but your independent variable becomes the log GDP. And you have to be careful that once you get the outcome, when you get the results of your model, you have to interpret it accordingly, especially if it's the outcome variable that has been transformed, then whatever estimate you get, you have to back transform it to the original scale to give it meaning. So another example, same example where this is the model corresponding to that example. So when you apply the regression model, as we see over here, these are the estimates that you get. You get the coefficient 10.43 for log GTP and the constant. And the way you would interpret is like a regression coefficient for every 1% if you say 10% increase in GDP per capita, the percentage urban population, you multiply this coefficient by this number 0.953 is the log of 1.10, which is the addition of 10%. So the every additional 10% increase of GDP increases the percentage urban population by 0.99. So if this had been in the original scale, then the interpretation would have been for every 1%, or we can multiply it accordingly. For every 1% increase in GDP capita, if the coefficient was 10.4, then it would mean that simply the urban population percentage increases by 10.4. For a 10%, every 10% increase, it would have been 104.3. So you would have interpreted it that way, but because you have log transformed, you will also use the appropriate coefficient to transform and interpret the outcome. In this case, it is 10% increase. It is in the log scale, so it will be log 1.10. If it had been a 10% decrease, then it would have been log 0.90 as a factor multiplied to this coefficient. So the other transformation that are used in literature, the square root transformation, it is again to reduce right skewness in count data, especially it is used in count data. So for example, bacterial counts and CD4 cells counts. Uh, uh, in these kinds of, especially incidence, mortality kind of data, you use the square root transformation and transform it non-normal data to normality, and you can apply models like Poisson distributions and Tobit distributions by applying these square root transformations. Reciprocal transformation. The reciprocal, here again, the disadvantage of the reciprocal transformation is you cannot apply it when you have observed, especially with the outcome variable, when you have observed values as 0. But it is very, very useful when you have data with very high variability. That variability is the cause for that skewness. So serum creatinine is a good example. You have units where the range of units is so wide that you may have individuals with very small or very high values naturally occurring. And by taking the reciprocal, you can apply your models and your tests. So that's it with the assumptions.